In this video, we are going to start a review of sections 4.2 and 4.2 up to 4.6 in the text. So in this video, we are going to focus specifically on bases. All right, so recall our definition. We say that if H is a subspace of a vector space V, that if we have a set of vectors B1 up until BP, that's a basis for that subspace H if there's two things that we need. The first is that set of vectors it needs to be linearly independent. So that set of vectors is linearly independent. And the second condition is, well, the vectors have to span our subspace H. So that's another way of saying that every vector B that's in the subspace needs to be a linear combination of those basis vectors. Okay, so that was our definition of a basis. Okay, the one big theorem from that section when we first talked about what a basis was is the spanning set theorem. So remember that what this said was, if you have a set of vectors v1 up to vp, and you consider the span of those vectors. So the span of a bunch of vectors is a subspace. That's something that we've shown. I'm going to call that subspace H. Okay. The first part of what the spanning set theorem says is, if there happens to be one of those vectors, vk, that's a linear combination of the others, then if you form this new set, which means if you just remove that vector vk from your list of vectors, then the remaining vectors still are going to span the subspace. Like, it won't change the span if you remove a vector that's a linear combination of the others. Okay, and the second part of the spanning set theorem said, well, as long as your subspace isn't just the zero vector, as long as there's more in it than just the zero vector, it'll turn out that some subset of it is going to be a basis. Some subset of it is going to be a basis for your subspace. And the key idea behind that was, and anytime you had a vector that was a linear combination of the others, you kept removing it until you ended up with vectors that were linearly independent. Because once they're independent, and if the span hasn't changed, well, they're satisfying both of the properties that we need for something to be a basis. Okay, so let's start taking a look at some practice problems. So these are geared around standard V4 from our syllabus, which is about finding a basis for a given subspace. Okay, so here's a practice problem from one of our worksheets, which says find a basis for the subspace H of R3 that is spanned by these four vectors. So if I take the span of those four vectors, that's some subspace. I want to find a basis for that. And then it asks, well, what is the dimension? What is the dimension of H? All right, and it says, be sure to explicitly verify that your set satisfies the conditions of being a basis. So we will have to verify that it's linearly independent and that the span is still the whole subspace. Okay. So in this video, I'm going to take a look at two practice problems that are like this. The first one I will work out. The second one, I'll give you an opportunity to pause the video on your own. Although if you'd like to do that for this one, you are more than welcome to if you'd like to try it before I go over. Okay. So how can I do this? I'm actually going to talk about two ways of solving this. So solution one. So what I can do is I can put all these vectors into a matrix. So the first vector, 1, 1, 0, second vector, third vector, and the fourth vector, we put them all into a matrix. And then we can row reduce it to see where the pivots are. So I'm going to go ahead and tell you what it row reduces to. Okay, I'm going to trust at this point that we are probably pretty good with our row operations. I'm going to tell you what it row reduces to. So you'll get 1, 0, 0, 0, 1, 0, 0, 0, 1, and then 1, negative 1, positive 1. I've actually reduced this all the way to RREF form. Okay, so at this point I can see where the pivots are. It's these three ones in the three rows right there. Okay, so I noticed that this last column doesn't have a pivot. And because of that, it's going to be a linear combination of the other columns. In fact, the last column, if I were to call that V4, well, if I think about these values here, it turns out that that fourth column is, 1 times the first column, and then minus 1 times the second vector, and then plus 1 times the third vector. Okay, and if a vector is a linear combination of the other vectors, and that's happening in this reduced form, well, that's still going to be true even back in the original. You could check it, but even in the original, this last column vector satisfies this same relationship. It's the first vector minus the second plus the third. Okay, all right. So what I can say now is by that spanning set theorem, since V4 is a linear combination of the other vectors, removing it doesn't change the span. Removing it doesn't change the span. Okay, so nice. So that'll leave us with the first three vectors. So let's consider the first three vectors. I'm going to call them V1, V2, and V3. So those first three vectors. And I'm going to go back to the original vectors here. So V1, V2, and V3. I'm going to go back to those original vectors. Okay. Well, those first three vectors, when I put them into a matrix and I reduced it, there happened to be a pivot in each one of those columns. Again, if I ignore the fourth one, because now I've removed it. So if there's a pivot in each column, that means those column vectors are linearly independent. They are linearly independent, since their corresponding columns have pivots. At this point, now there's a pivot in each remaining column. So pivot in each remaining column. In each remaining column. That's another way to say that. Okay, so the vectors we have, they're linearly independent. That's one thing that we need for it to be a basis. And the span hasn't changed, so their span is still the whole subspace H. Well, collectively, those are the two things we need for it to be a basis. So together, this means that the set of vectors we are down to, just V1, V2, and V3, well, this is a basis for our subspace. Awesome. Cool. All right, so we have found a basis for our subspace. Okay, and then it asks, well, what's the dimension? The dimension. So remember, the dimension of a subspace is the number of vectors in the basis. So in this case, the dimension is 3. Okay. All right. So I mentioned that I was going to solve this in more than one way. So let me talk about another solution to this. So a second solution. Okay. So sometimes we can get a little lucky, and if we can tell just by looking at the vectors if one of them is a linear combination of the others. So if I label this fourth one V4, if I could sort of tell I'll say by inspection, that just means by looking at it. If I could tell by inspection that V4 happens to be the first vector plus the third vector minus the second. Again, I may not always be able to tell that just by looking at it, and that's where this first method comes in, which is more systematic. But if I was able to tell that just by looking at it, well, we can remove it from the list. So we remove V4, which won't change the span by the spanning set theorem. So I'm justifying why. It's the spanning set theorem that tells me that if I remove a vector that's a linear combination of the others, it won't change the span. Okay, so bullet point, span has stayed the same. And now I would have to show that those remaining vectors are linearly independent. How could I do that? Well, I could form the matrix. I could form a matrix that has those vectors as the columns. V1, V2, and V3. And look to see if it has a pivot in each column. Look for pivots in each column. It'll turn out that it will have pivots in each column, so those remaining vectors are going to be linearly independent. So I'm just going to put a dot, dot, dot there, because the row reduction will be very similar to what we had here, except we don't have to worry about having a fourth column. So it makes the row reduction a little bit easier, because we have less entries to work with. But we'll get the same result. It's going to be a basis. All right, so let's flip the page, and let's take a look at another example. Okay, but this time I'm going to up the difficulty a bit, because now we'll have a subspace of P2. Remember, P2 is a set of polynomials of degree at most 2. Okay, and I'm forming the subspace that's spanned by these 3 polynomials. And again, it asks me to find a basis for this subspace, and then what's the dimension? Okay, so I first want to give you an opportunity to try this one. So I want you to pause the video for about 3 minutes to try this one on your own first. So 4, 3, 2, 1, pause it and try it on your own for about 3 minutes. It's a really good practice for you to try it on your own and see, well, how well do you understand this idea? Or, you know, if you're a bit stuck, how can you apply things that you've seen before, review your notes to tackling this question? All right, so hopefully you did that. Hopefully pause the video to try it. Let's talk about it now together. Okay, so one of the things I can do if I'm not working with vectors is we can convert them to vectors using coordinate vectors. So let's convert these things to coordinate vectors. If I'm going to convert to coordinate vectors, there's got to be some basis that I'm referring to. Let's do it in terms of the standard basis. The standard basis for P2. Recall that the standard basis for P2, usually we call the standard basis E. This is a script E, and it consists of the polynomials 1, t, and t squared. So if I needed the standard basis for P3, I would have also included t cubed, and we would go and so on if I needed a higher degree thing. Okay. All right, so let's review. How do we do this? So for example, if I wanted that first polynomial, which is just 1, I need to figure out, well, how do I write it as a linear combination of these basis vectors? So 1 is what times that first polynomial in the basis, plus what times that second polynomial t, plus what times that third polynomial t squared. So what are the weights that we'd pick to make this work? Well, we'd pick 1 here, and then 0 there, and then 0 there. Okay, so at this point, I take those weights, and I put them into the vector, and that gives me the coordinate vector. Okay, so the way I denote this is I write my polynomial, which is 1, in brackets. I put the basis as a subscript. That's a notation for a coordinate vector. And then I form the vector that has those entries as the weights. Okay, so this first entry becomes the first weight becomes that first entry of the vector. And then this next entry will be the next thing here. And this last weight, different color, this last weight becomes the last entry of the vector. Okay, so that first weight was a 1, then I had a 0, and then I had a 0. And that's my coordinate vector. Okay, so if I do the same thing for these other polynomials, the next one is 3t squared minus 6t minus 1. If I write its coordinate vector in terms of this basis, let's see. I got to be careful about the order. The way that I'm writing the order of these basis elements, I have put the 1 first. So I need the weight that I'd put in front of the 1 first. In this case, that's going to be a -1. And then I need the weight in front of the t, which is -6. And then I need the weight in front of the t squared, which is a 3. So -1, -6, and +3. Okay. If I had wanted to order these basis elements in a different way, that would be fine, totally fine to do, but as long as I say consistent anytime I form my coordinate vectors. Okay, so that would result in these entries, switching spots, but as long as I stayed consistent throughout, it's totally fine. Okay, all right, we got one more polynomial to go. So the last polynomial is this one. So this one I should FOIL it out so I can see its coefficients. This becomes t squared minus 2t plus 1. So let's write that coordinate vector t squared minus 2t plus 1. That polynomial's coordinate vector, well, the constant term is 1, the coefficient of t is negative 2, the coefficient of t squared is 1. We're going in that order for these coordinate vectors. Nice. So now that we have vectors, we can work with them like we did in the last problem. We can form the matrix with these as the columns. So 1, 0, 0, negative 1, negative 6, 3, 1, negative 2, 1. I can form that matrix. And then I can row reduce it. I'm going to tell you what it row reduces to. That becomes 1, 0, 0, negative 1, 3, 0, 1, 1, 0. This time I'll just stop at echelon form because that's good enough to identify the pivots. There's a pivot at this 1 and at this 3. So I can see that this third column does not have a pivot. And what that means is, well, this third column vector is a linear combination of the others. So if I backtrack in terms of my original polynomials, it means that the third polynomial is a linear combination of the first two. Okay, it's not even necessary for me to have to find the weights. Just the mere knowledge that I now have that it's a linear combination of the others means that we can remove it from our list. So I'll say by that spanning set theorem, we can remove P3 without changing the span. Okay, so I'll put a bullet point next to that. That's one of the things that I need to show that what I'll have left is a basis. The polynomials P1 and P2 still have the same span. They span the whole subspace H. So what's left for me to check is now if I think about the polynomials P1 and P2, if I think about the polynomials P1 and P2 that are left, are they linearly independent? So I could do that by looking at this matrix and being like, oh, when I throw out the third column, now the remaining columns, there's a pivot in each one, so that means those vectors are linearly independent, and that would mean those original polynomials, third one removed, are linearly independent. I definitely could do that, but there's also a very quick way to do it just because I have two things left. If I have two elements, they're linearly independent as long as they're not multiples of each other. Okay, so this, I can say it is linearly independent since we have two elements and they are not multiples. They are not multiples. That makes them linearly independent. Okay. If I had more than two elements, well, then just checking for multiples isn't good enough because maybe one of them is a linear combination of the others. And then using pivots would be the fastest way. Okay, so let me just put in parentheses that we could also say that their corresponding columns have pivots. Their corresponding columns all have pivots. And that would be another way to check that they're linearly independent. Okay, so it has that span property because the span didn't change. And now these polynomials are linearly independent. So this implies that the set P1, P2 is a basis. It is indeed a basis for my subspace H. Awesome, and I have a basis. Last thing it wanted was the dimension. The dimension is the number of elements in the basis. There were two polynomials in the basis, so the dimension is 2. And that's my answer.